Okay, so here we're going to talk about just advection, and then I'm going to leave the spread and random mixing processes until class. So to predict advection, that is movement with flow, whether it's in a stream, in the groundwater, and air, we need velocity and direction. So what direction is the water or the air moving, and then how quickly is it doing that? We also need concentration, so how much of the pollutant is in the water or the air that is being moved in that direction. So we combine these two things to figure out the flux density, which is not a term that I'm a huge fan of. It's a little bit confusing. You can think of it just as flux, if that makes it easier for you. And it's abbreviated typically as J, right here. And it's the mass of a chemical that moves through a given cross-sectional area per unit time. So if you just sort of glazed over when I said that, I have a little animation to try to explain that to you a little bit better. I know sometimes when I hear a lot of things like that, I sort of phase out. Okay, so here is a pipe with water flowing through it. You can see the flow direction here going this way. And here's a cross-sectional area of that pipe. And let's say we introduce some pollutants here, purple things, and they're floating downstream with the water. And here at time 0, so we're going to start our watch and time pollutants moving through this cross-sectional area over a minute, 60 seconds. So here we go. We've got 15 seconds, things moving downstream. We've got 2 particles passing through the cross-sectional area at 30 seconds. 45 seconds, we've got a couple more, and then by 60 seconds, which is when we're stopping our watch, we had these 5 particles pass through the cross-sectional area of the pipe. So if we were interested in cross-sectional density, or if we were interested in flux density, we would calculate that. If each particle weighs 5 milligrams, say, then we have the mass of those particles, 5 milligrams times 5, and these, so 25 milligrams passed through this cross-sectional area in 1 minute. So that is what flux density is. It's how much of a pollutant is passing through a cross-sectional area of whatever it is you're interested in, whether it's a pipe, a stream, an area of groundwater, in a unit of time, a second, a minute, or an hour. Okay, and then I just did the multiplication for you there. Okay, so in terms of equations, this is what that ends up looking like. So you've got flux density here is equal to the concentration, because usually we can't count particles moving through a cross-sectional area, but we can measure the concentration. So that's mass per volume multiplied by the velocity of what the pollutant is moving in, whether it's a stream or a pipe or the air. And then the flux density ends up being in units of mass per area per time, just like we saw in that little pipe example. Okay, and like I said, we aren't able to count particles moving through a cross-sectional area, so what we usually have is a situation like this. With smoke moving through the air, we pick a cross-sectional area of interest, a meter squared, a centimeter squared, something like that. We know the predominant wind direction, on average, the wind velocity, and we know on average smoke concentration, and we use those 2 pieces of information to calculate the flux density. Okay, and here is an example that I'm going to do separately for you in the next little video. So you don't really have to read it right now, just giving you a heads up. This will be the last video that you'll need to watch. And then we'll talk in class about mixing processes. So again, thanks for watching.